Okay, ladies and gentlemen, in this episode we're going to look at wavefront diagrams and how they are affected when you undergo reflection and refraction. Okay, so what we're going to start with is we're going to start with what a basic wavefront diagram is. A wavefront diagram is essentially, imagine you were looking down on a wave from above moving across the water. Then what you would see is you wouldn't actually see the uppy downiness of the wave being transverse, but what you would see is you would see the crests of the wave. So imagine these are the crests or troughs of the wave. Okay, then these would be traveling along. They're roughly equal in length, and in fact they are exactly equal in width, and they should be equally spaced along here. Okay, remember the distance from here to here. Okay, just pop that on like that. That distance there, that is a wavelength, and we denote that using lambda. Okay, so that's a wavelength there. Okay, now generally speaking, these diagrams are quite tricky to follow. So what we do is we put an arrow down the center to tell us where our wave is going. Okay, so this goes down the middle, and each of this arrow is at right angles to the rest of the line. Okay, so this little bit here, that's a right angle. Okay, so this is the direction of propagation, and these are your crests. Okay, so here we go. This is a standard wavefront diagram. Nice transverse wave progressively moving along. Though it doesn't need to be transverse, this could equally be longitudinal, and these could be compressions. It doesn't have to be a transverse wave. Okay, now the problem arises if we hit a barrier of some description. So let's get ourselves an object to bump into. There we go, and let's give it a color. So click on that, and there we are. Lovely. Okay, so what we want to do is we want to hit this and bounce off. Alright, so we should know already that in order to do anything with light or waves or anything like that there, then at the point where the ray is going to hit or the waves are going to hit, which is here, we need to draw a normal. Okay, so do that by getting myself a little line. There's a line, but this line should be a dashed line. Okay, because it's imaginary, just thin it out a bit. Okay, so there's my normal. Alright, so my incoming angle, my angle of incidence, which is here. Okay, we call that I, or angle of incidence. I'm going to have to equal my angle of reflection. Okay, so I'm going to copy that and rotate it around a bit. So doing my angle of reflection, I'm going to call that R. Okay, so my ray is going to, my wave is going to come out along this line. Okay, I keep saying ray because rays and waves, much the same thing. Ray diagrams work exactly the same way. So there we go. Okay, because I'm not changing material, okay, this out here is maybe air or water or whatever, then whatever it bounces off into is still air and water. So there's going to be no change of speed of the wave, there's going to be no change of frequency, which means there will be no change of wavelength. Okay, so the waves that come off the other side will be the same width, and they will be the same spacing apart. Okay, now that's quite difficult to do on screen, but in an exam, take the time, get the ruler out, and just make sure that these are nice and equally spaced. Okay, so the wavelength before is equal to the wavelength after. Okay, now I'm just going to color these lines in slightly different color just so that we can see exactly what's happening. Okay, so make them a nice orangey color. Okay, now as this wave comes in towards here, the wave obviously can't go into the material, so it gets kind of cut off there. It's absorbed by the material. Okay, and this one goes in and it's absorbed a bit more, and this one absorbed a bit more, and so forth until the wave is fully absorbed by the material. Okay, then the wave coming out is exactly the same. So you basically try and draw them all the way back, equally spaced to where they could have started, where the waves possibly struck the wall. Not so much with that one. And then we just cut off the bits that can't exist, the bits that are inside. Just remove those bits. Okay, or don't draw them in the first place if you're using a ruler in the exam. And there you go. That's your reflection set. That's your reflection done. Now, to be honest, in the exam, you would get away with not having this section in here at all. Just having in, out, because they'll be looking for the wavelengths the same, the width the same. Okay, and the angle of incidence equal to the angle of reflection. Okay, so that's reflection. Refraction, much the same idea, to be honest. So let's take our wave, pop it over here, okay, and let's send it into an actual material. So this time it's not a solid boundary, it's something like a glass block. Okay, the wave can actually travel into it. So this was light, or in the case of water, we'll go from deep water to shallow water. Okay, so out here, let's assume this is a deep water situation. They like these ones. So this is deep water, and this is less deep, also known as shallow. Right, now, I know none of you out there would ever be accused of being shallow, but I'm sure you've heard the word before. Okay, so simple idea. As we come in, again, first thing we do is we get together a little normal. I need to get rid of those ROMs. Okay, so that's our normal sorted out. And we should know at this stage in our revision that as light travels in, or as any wave travels in, it wants to go straight on, but because it's slowed down, because it's in shallower water, it slows down and bends towards the normal. So it'll take something like that path. Okay, happy? Good stuff. Alright, now, in here that means we have to just change our waves, because remember this has to be at right angles to our ray, so our wave is like this. Okay, same width, but this time it's slowed down. Remember from last episode that v was equal to f lambda. Okay, that v equals f, and then the annoying comics have to change the symbol times lambda. Okay, so we said that the speed of this wave was going to go down. Now whatever's making this wave happen continues to make it happen at the same rate every second, so the frequency must stay the same. So that means that the only way for this equation to remain balanced is if the wavelength also goes down. Right, so when you slow your wave down by refraction, then your wavelength should become less. Okay, so you pop those closer together. Okay, constant wavelength between them, but it should be less than the original. And again, this would be enough in the exam to probably get you the mark, but always a good idea to continue your ray so that it, or your wave, so that it comes in. Okay, cut off the end parts, okay, because those are the bits that aren't going to stay nice and straight. And then using your ruler, put on the ends here that are at right angles to the, or along the same line as the other ones. That one there is actually okay. Maybe slightly, a tiny little bit on the end of that changes. Okay, and we can do one more just for the sake of completeness. And there, nice big wavelength there, and then we cut the end off that. Take that up there. And there you go. That is your refracted wave. Okay, going out the other side is exactly the same story. Okay, just the opposite way around. As we leave, we will speed up and bend away from the normal. So we want it to go this way, but we have to speed up and head away from the normal. So we're going over here somewhere. Our wave will therefore have to rotate slightly to go along that. And because of the fact that it has speeded up, the wavelength increases again. Okay, and that's wavefront diagrams. See you next time.